everyone, welcome back to the channel Mining Engineering. This is lecture number 3 on the topic Geographic Information System. In the previous lecture, we have discussed Geographic Coordinate System, what are the data, hence now we are able to uniquely identify any position on Earth's surface by a pair of latitude and longitude. Now let's see what is map projection. It is a method to represent three-dimensional surface of the Earth on a flat 2D surface. Map projection is a systematic transformation of the latitudes and longitudes of locations on the surface of a sphere or an ellipsoid into locations on a plane. Project from the Earth's surface to a developable surface such as a cylinder or cone and then unroll the surface into a plane. Basically, map projection is a method in which this three-dimensional system will represent that thing into a plane 2D surface. So, this is the method. The graticals of a geographic coordinate system is projected onto a cylindrical projection surface. This is the thing. And this is the developable surface. This is done by the location of light source. If the light source is at infinity position, then the projection will be like this. At a pole, the projection will be like this, and at the earth center, the projection will be like this. This is called at infinity. The projection is called orthographic projection. At a pole, the projection is called stereographic projection, and at the earth center, it's called the economic projection. So, this is the Mercator projection which we are now using in our map. There is one interesting fact that we normally don't know. There is a distortion in the map. This map is not actually correct if we compare the size of the countries. If we see in this map, this is the Greenland and this is our Australia. I see the size of Australia and that's the size of Greenland. We can compare the Australia country is looking smaller as compared to the Greenland. But that's not the actual fact. If you compare the size of Australia with the size of Greenland, Australia is much more bigger as compared to the country Greenland. This thing this thing happened because of the distortion while we are projecting the three-dimensional thing into a two-dimensional surface. So, what is the distortion? Earth's surface cannot be represented on a plane 2D map without distortion. Distortion occurs with respect to area, shape, distance, and direction. So, if area are shown correctly, then there will be distortion in shape, distance, direction. Local shapes are shown correctly, then other parameters will be distorted. Preserve distance along some points or lines. All directions are shown correctly related to the center. So distortion will occur if we fix any of these parameter, then other parameters will vary. A map can never preserve all of these properties at once. Also, a compromise can be made among such that none of these properties are truly preserved. If we compromise all of these four parameters to represent a more or less accurate map. So, distribution, there is one indicatrix. Distance indicatrix is a graphical tool which helps us visualize the distribution. So, in this map, we have preserved the shape of all the countries. Here, the area are preserved. So, see the shapes are distorted in this map. Here we have compromised all of these four parameters and a more or less accurate maps is represented here. Different classification. So as per the developable surface, azimuthal, conic, cylindrical, light source location, orthographic, stereographic, chronomic, properties preserved, conformal, equiarea, equidistance, compromise, orientation of developable surface, normal, transverse, oblique, equatorial, polar, oblique, contact with developable surface, tangent and secant. Classification of light source. This is orthographic projection where source of light is at infinity. This is stereographic source. This is the chronomic source and the projection surface 1. This is secant projection. This is projection surface 2. This is the tangent projection. So as for the tangent projection, this is the cylindrical projection. This will be the conical projection. This is the azimuthal projection. And second, this is cylindrical, conical, and azimuthal. Classification as per the contact, the line of tangency between a projection surface and the surface of the globe is called the standard line of the projection. Along the standard line, there is no distortion. So, if you are projecting as per the tangent, so this is our projection line. So there will be no distortion at this position and there will be most distortion at this position. So at the equator there will be less distortion and at the poles there will be high level of distortion. When the projection surface intersects the globe, you get a second projection with two standard lines. So at this point, no scale distortion and there will be most distortion at this point. Classification properties preserved. Conformal is orthomorphic, preserves local shape by using correct angles. The angle between them is the same as between the intersection of any two lines on the map and their counterparts on the sphere. Latitude and longitudes are perpendicular to each other. For example, Mercator, stereographic, Lambert conformal conic. Second one, equal area homolographic projection. Ratio of areas on the earth and on the map are constant. Commonly used in GIS because of importance of area measurements. Used for thematic or distribution maps. For example, Albert's conic, Lambert's azimuthal, Lambert's cylindrical equal area. Next one, equidistant. Here, preserves distance on scale between some points or along some lines. No map is equidistant, that is, has no correct scale everywhere on map. Important for long distance navigation. For example, azimuthal equidistance. Compromise. This projection system tries to seek a balance between distortion, for example, Robinson Miller cylindrical. Classification as per developable surface. Azimuthal projection, also called a planar projection. This is called the planar projection, where the projection is done on polar, equatorial, and this is the oblique projection. The polar projection, then the map will look like this. This is the world map. We can say this is the world map as per the polar projection, azimuthal polar projection. All azimuthal projection can maintain true distance from the center point. Grid circles through central point are represented as straight lines. If center is at the poles, meridian are the straight lines. Normally, one hemisphere or a portion of it is represented by this azimuthal projection. Gonamic azimuthal projection, neither conformal nor equal area. Shortest distance between two poles on a sphere are shown as straight lines, used widely in air navigation, should orient the center of the map at the point of interest. Heavy distortion as we move away from the center of the map. Conic projection, useful for representing the mid-latitudes. The developable surface is a cone which is cut along any meridian to produce the final conic projection, has straight converging lines for meridians and concentric circles arcs for parallels. As for the conic projection, our old map will look like this. Deviation can be minimized in a region of interest by using a second developmental surface. Here the region of interest should lie largely between two standard parallels. Polyconic projection, mainly conic developable surfaces are used, each having a different standard parallels. Projection unsuitable for large areas on a single sheet. Distortion increases as you move away from the central meridian. Survey of India uses this projection system for its topographical sheets. Each sheet has a different central meridian. Lambert conformal conic projection. For these standard parallels is at 20° north and 50° north. Albert's equal area projection, the equal area for the standard parallels is at 20° north and 50° north. Classification as per W surface cylindrical projection. Is a transverse. Cylinder has line of tangency to the meridian. Is oblique. Cylinder has line of tangency to the other point on the globe. Is normal. Cylinder has line of tangency to the equator. Now comes the Mercator projection. Is a conformal. Distortion is minimum near the standard parallel, here at equator. Distortion is very high towards the extreme ends, here at the poles. The distortion is minimum, and here at the pole area, the distortion is maximum. Gulf-Peters equiarea projection. This is equal area projection. Cosine projection is pseudo-cylindrical projection, equal area, interrupted at the oceans to put an emphasis on land areas. Transverse Mercator projection is still conformal. One longitude is well represented without distortion. That is this longitude. Now let's see what is UTM, Universal Transverse Mercator Coordinate System. It's one of the very important projection coordinate system because in our daily use we use this projection system. Here, like this one longitudinal zone, the world is divided into 60 narrow longitudinal zones. In the universal transverse Mercator projection system, it divides the world into 60 narrow longitudinal zones of 6 degrees, which are numbered from 1 to 60. Each zone is a transverse cylindrical projection with a unique central meridian. Zone number 1, that is 180° west to 174° west, and the zone number 60, that is 174° east to 180° east, and the latitudes from the latitudes bands map from 80° south to 84° north. It's represented by an alphabet like this. So this is the UTM, Universal Transverse Mercator map. Each quadrant is 6° wide, 6° wide and 8° tall, except this X, which is 12° tall. UTM uses false value easting and northing to derive coordinates in meters. So this is the Universal Transverse Mercator coordinate system. Here we have divided the world into 60 narrow longitude, 60 narrow bands from here to here, and 20 um, quadrant of 12° of 8° tall, except the X1. We will go into details in the next lecture.